Now we will talk about physical properties of haloalkanes and haloarenes in this video lecture. In physical properties, we would be discussing physical state, color, odor, melting point and boiling point, solubility, density and relative density of haloalkanes and haloarenes, right? So here we'll talk about haloalkanes, and there I'll mention about haloarenes. So talking about the physical state, color and odor, as the size of the alkyl group increases, or as the number of carbon atoms increases in haloalkanes, their physical state changes from gases to solids, right? So lower haloalkanes like methyl chloride, methyl fluoride, ethyl chloride, all these are gases. But as we move right towards higher haloalkanes, they changes to liquids and then to solids. Up to C18, right? Up to C18, the haloalkanes are liquids, right? Beyond C18, these are solids, right? And about odor, most of the haloalkanes, they have sweet odor, but higher haloalkanes, the haloalkanes that are solids, they are odorless, they don't have any odor, whereas up to C17 they have sweet odor, right? Talking of haloarenes, physical state, they are either liquids or they are odorless solids, right? They are either haloarenes are colorless liquids or crystalline solids. They are colorless liquids or crystalline solids. Crystalline solids. Now, second property is that of melting point and boiling point, right? Melting point and boiling point, right? Melting point is we melt any substance when we heat it, right? And we know that melting a solid means with the help of heat you break, or you basically what you are doing is with the help of heat the constituent particles of solid will move apart, right? So same happens in boiling point also. So melting point and boiling point depends on the force of attraction between your constituent particles, right? And in case of haloalkanes and haloarenes, we know that they can form hydrogen bondings, right, with water, right, because of Cl, because of highly electronegative atoms, but we have no or very less hydrogen bonding, right, in case of haloalkanes and haloarenes, right? But we know that they are polar molecules. Haloalkanes and haloarenes have a polar bond, so they are polar molecules, but their polarity is also very less, right, such that they don't interact very well with one another. They don't have high force of attraction due to dipole-dipole interaction between one another, right? So let's look into their melting point and boiling point, and it also depends on the size of the alkyl groups and the size of the halogen atom, right? So this is your haloalkane, right? X stands for alkane, this stands for alkyl group, right? So melting point and boiling point increases with increase in size of the halogen, right? So melting and boiling point increases, right, with increase, up arrow means increase in size, with increase in size of X means halogen atom, right? Similarly, if we talk about alkyl groups, keeping your halogen same, right, your melting point and boiling point will increase with increase in size of R group, right? That is alkyl group, right? For example, methyl, ethyl, propyl, butyl, right, heptyl, pentyl. So what we are basically doing is we are increasing the size of the alkyl groups, right? Bigger is the alkyl group, more is the melting point and boiling point, right? So what could be the reason? Because we see that in both the cases, as the size of the alkyl group or the size of the halogen atom increases, the melting point and boiling point are also increasing. The reason being that as the size increases, right, as the size of the alkyl group or the halogen atom, right, alkyl group or the halogen atom, as the size increases, the intermolecular force of attraction or the van der Waal force of attraction increases, right? As the size of either of these increases, it would be able to interact with more number of neighboring molecules, right? So when it will interact with more number of neighboring molecules via van der Waal force of attraction, that means now you have more molecules interacting with one another, right? So now you have to give it more heat, right, in order to melt it or in order to boil it, right? Same happens with your HaloArenes, right? We'll just talk about HaloArenes. Let's first talk about HaloAlkanes. So we said that with increase in size of the alkyl group or with the increase in size of the halogen atom, the melting point and boiling point increases. Why? Because as the size increases, it will interact with more number of neighboring molecules, right? Thereby van der Waal force of attraction will increase, right? That means now it is interacting with more molecules, right? So force of attraction via van der Waal interaction increases. Thereby now you need to give more heat, right, in order to melt it or boil it. The third thing is with branching. How does branching affect? How does branching in HaloAlkanes affect your melting point and boiling point, right? If we talk about branching, let's take example of molecule CH3, CH2, CH2, CHBr. This is your 1, 2, 3, 4 normal and butane, right? Now this is your straight chain HaloAlkane. Now if I branch it, right, if I branch the same molecule, like this, right, this would be 1, 2, 3, right? The name of the compound is 1-bromo-2-methyl-propane, right? This is 1-bromo, methyl group is at second carbon atom, 1-bromo-2-methyl, 3 carbon atoms, propane. You should know the IUPAC naming convention, right? So here branching has increased, right? Now let me just branch it further. Let's further branch it. Right, this is your tertiary butyl, right, or 2-bromyl, 2-bromo, right? Let's say 1, 2, 3. This is the longest chain. So this is 2-bromo, 2-methyl propane, right? 2-bromo, 2-methyl propane, right? This is maximum branching is in this molecule, right? Then there is no branching in this, right? It is found that the boiling point of straight chain HaloAlkanes is maximum, right, and boiling point of branched chain HaloAlkanes is minimum. That means with branching your boiling point and melting point decreases, it goes down, right? What could be the reason? If you look at this molecule, this is a straight chain molecule. You can see it can interact with more number of neighboring molecules. Here this is now more compact. As I'm increasing the branching, the molecule is becoming more compact, right? Or the surface area is decreasing. Like you can see the surface area of this is more, then surface area of this compared to this is more, because now this has compacted. if you look at this, the surface area of this, the most branched molecule, is minimum, right, compared to all three, right? So this is most compact and its surface area is less. So when surface area is less, the van der Waals force of attraction decreases, or now it would be able to interact with less number of molecules. This would be able to interact with more number of neighboring molecules, right? And this, due to its less surface area, will interact with less number of molecules, right? So interaction is decreasing, right? That means now less molecules are interacting in case of branched chain haloalkanes, right? So less interaction means less, you need to give them less heat in order to melt it or boil it, right? So due to increased branching, right, the surface area decreases, due to which the interaction decreases, right? The branched chain haloalkanes interacts with lesser number of neighboring molecules, right? So their melting point and boiling point becomes less. Right, now let's talk about melting point and boiling point of haloarenes. In case of haloarenes, the same thing, as the size of the halogen atom increases, their melting point and boiling point also increases, right? If we talk about size of the halogen atom, it's fluorine, bromine, chlorine, iodine, right? Size increases down the group. Right, this is how they are arranged in periodic table. So as you move down the group, their size increases, right? So if I take this compound or this compound, right, size of Cl is less compared to iodine, right? So boiling point and melting point increases with increase in size of the halogen atom. Melting point and boiling point increases, right, with increase in size of the halogen atom, right? So boiling point of this, right, would be more than the boiling point of Cl. Why? Because the size of iodine atom is more, right? So with increasing size of the atom, your boiling point and melting point increases, and the reason could be the same, because as the size of the halogen atom increases, it would be able to interact with more number of molecules, thereby increasing the melting point and boiling point. Now in case of haloarenes, one important thing that we need to look into is the melting point and boiling point of its isomers, right? Isomers, melting point and boiling point of dihaloarenes, like melting point and boiling point of dihaloarenes. This, right, and then you have, this is your ortho isomer, ortho dihaloarene, ortho dichloroarene, this is meta dichloroarene, this is para dichloroarene, right? So when you compare the melting point and boiling point of ortho, meta and para isomer, the melting point and boiling point of para isomer would be maximum, right? Melting point and boiling point of para isomer is maximum. Now what could be the reason behind it? The reason is symmetry, right? The reason is symmetry, because if we talk about the crystalline lattice, right, the lattice of symmetric molecules, any symmetric molecules, right? Okay, if you look at this is less symmetric, right? You cannot divide it into exact two halves. If you divide it into exact two halves, both the halves are different, right? And if you divide this into two halves, again it would be different. So they don't have any elements of symmetry, kind of. But this isomer can be divided into exact two halves from here, right? It can be divided into exact two halves. So para isomer is most symmetric. Since it is most symmetric, its packing in the crystal lattice, right, would be more efficient, right? They are well packed, and since if the constituent particles are well packed, the force of attraction with other constituent particles would be more, right? So due to which, since its force of attraction with other constituent particles is more, right, so you have to give it more heat, right, in order to melt it or boil it, right? Because in case of para isomer, the forces of attraction is high, right, because of its symmetry, right? Because of its symmetry, firstly it's well packed, right? Since it is well packed, so you have to give it more energy in order to unpack it, kind of, right? Or due to its well packing, it is able to interact with more number of molecules, right, surrounding neighboring molecules or neighboring particles, right? So since it is interacting with more number of neighboring particles, that is, force of attraction is high in case of para isomer, so you have to give it more heat in order to melt it or boil it, right? So that's why we say that melting point and boiling point of para isomers is maximum compared to the other two, ortho and meta isomers, because of its high symmetry, right? I hope this is clear. Now let's discuss about other important property, which is your solubility, right? Solubility of any compound, right? Talk of any compound, the solubility, right? If I'm dissolving any haloalkane, say methyl chloride, right, in water, right? This methyl chloride will dissolve in water only if it can interact well with the molecules of water. We know that water molecule has hydrogen bonding, right? They have hydrogen bonding between its constituent particles, between the molecules of water. Water molecules have hydrogen bonding between them. Now, if you talk about the melting point and boiling point of the solubility of methyl chloride in water, methyl chloride does not form hydrogen bonding with water, right? So it cannot interact with water, it cannot interact well with water, right? In order to dissolve in water, the interaction between methyl chloride and water should be same as interaction between water, right? Then only it will be able to break hydrogen bonding between water molecules and would be able to enter in between water molecules, right? Since it cannot make hydrogen bonding with water, right, so it would not be able to break already existing hydrogen bonds, right, between water molecules, and neither it would be able to make new hydrogen bonds with water, right, because there is no hydrogen bonding, right? So it is less soluble. And one more thing, we know that water is ionic, like this. It has hydrogen ions and hydroxyl ions. This is how we draw the structure of water. Water is ionic in nature. Since water is ionic in nature, right, and methyl chloride, its better word is not ionic, let's say polar. Water is polar molecule, right? It has polarities, negative and positive polarity. Similarly, your methyl chloride molecule is also polar, right, because of the CCl bond. It is plus and minus, but this polarity is very less, right? So it would not be able to interact well with water due to its polarity also, because we know that solubility rule is like dissolves like. That means if this is polar, solute and solvent both should be polar. If both are polar, then the solute would be able to interact well with solvent molecules and will dissolve in it, right? But here, since both are not like molecules, right? They are not same molecules, same kind of molecules. So by same kind, I mean they are not polar molecules. It is polar, but the polarity is very less, right? So interaction between water and methyl chloride is less. So it is very less soluble or almost not soluble in water, but it is soluble in organic solvents. Why? Because organic solvents are non-polar, and we know that like dissolves like, right? So interaction between non-polar or very less polar haloalkanes is more, right, with non-polar organic solvents. That is why haloalkanes are soluble in organic solvents, right? I hope this is clear, right? So they are haloalkanes are there, and they are slightly polar, like I said, right? But one thing many times has been asked, that they are slightly polar, but still they are immiscible with water. They do not dissolve in water, or they are immiscible with water, although they are polar, right? So what I've just explained, that needs to be mentioned there, right? You need to mention there that they can neither form hydrogen bonds with water molecules, nor that they can break already existing hydrogen bonds in water, right? That is why they are, although they are polar, but they are immiscible with water, because this polarity is very less, right? That they cannot make hydrogen bonds with water, nor they can break the already existing hydrogen bonds, right? Same is with your haloarenes. In case of haloarenes also, you have the same thing, right? They are insoluble in water, but they are soluble in all organic solvents like ethanol, diethyl ether, right? Their insolubility is due to their low polarity, right? Now why haloarenes are insoluble in water? Because again, same as haloalkanes, they are less polar. Their polarity is very less, right? Their polarity is less to the extent that they cannot form hydrogen bonds with water, right? Nor they can break already existing hydrogen bonds, because as I said earlier, that in order to interact with water molecules, they need to break already existing hydrogen bonds and start interacting with them, right? And they would be able to interact only when the interactive forces between water and haloalkane or haloarene is same as between water molecules, but their interaction is with water molecule is not same as between water molecules, right? So they are insoluble in water. Now these are the important properties, right? There are two more properties that we'll do in haloalkanes. First is density, right? Like we have studied here, we have gone through the size of the halogen atom. Size of the halogen atom decreases as the size of the halogen atom increases as we move down the group. So size of iodine is maximum, size of fluorine is minimum, right? Fluorine is smallest, iodine is biggest, right? So density of methyl iodide is 2.279, right? If we talk about methyl iodide, it's 2.279 density, right? And if we talk about bromide, right, any bromide, let's say CH3, CH2, CH2, CHBr, its density is 1 point something. The density is 1.275, right? So here the density increases with increase in size of the halogen atom. We know that size of iodine atom is bigger compared to your bromine atom, right? And the density of iodide is more compared to bromide, right? So we say that density increases with increase in size of the halogen atom. Same goes with haloarenes. The density increases, right, with increase in size of the halogen atom in case of haloarenes and haloalkanes. Now one more thing, relative stability, right? We'll talk about stability. When we talk about stability, we are more concerned with this bond, CX bond, in haloarenes and haloalkanes, right? If we talk about this bond strength, right, since we know that size of the halogen atom, in case of X we have fluorine, chlorine, bromine, iodine, right? We know that size increases as you move down the group, right? And as the size of the halogen atom in here as the size of the halogen atom increases, the bond length also increases, right? And we know that bigger bonds are weaker compared to smaller bonds. Now here, size of iodine is maximum, right? So bond length of Ci is maximum, right? Bond length of Ci in any halogen or haloarene is maximum. Let's talk about its haloalkanes more. So this is observed more in haloalkanes, right? So bond length of Ci, right, in any haloalkane is maximum, right? So bigger bonds means weaker bonds, right? So Ci bonds, right, is weakest, right, in case of haloalkanes, is maximum and is weakest, right? Whereas if we talk about CBr bond with bromine atom, we know that bromine is smallest, right? Since bromine is small, so bond length is minimum with carbon among all these halogens, right? Since bond length is minimum, so bond strength is maximum. Why? Because smaller bonds are stronger, right, as compared to bigger bonds, right? That is why double bonds are stronger than your single bonds, because single bonds are bigger, right? Same thing applies here. Due to increasing size of the halogen atom, the bond length increases. Size of the iodine is maximum, right? So its bond length with carbon would be maximum, right? So bigger bond, this has maximum bond length, so it would be weakest, right? That is why iodides, when placed in light or in sunlight, they appear reddish brown. Why? Because iodides break to give you iodine, right? Because this bond is weakest, right? So haloalkanes that contains iodine bond with iodide are unstable. They have less stability. Why? Because of this bond strength. Their bond strength is weak. Bond strength is weak because of maximum bond length, right? So that is why when iodides are placed in air, they will appear reddish brown, because they break to give you iodine gas. Ri, right, in light will break you to give iodine vapors, right? Due to this, it appears reddish brown, right? So it becomes violet or brown on standing, right, due to decomposition. Due to this iodine gas, it will become violet or brown on standing due to evolution of iodine gas, right? I hope all this is clear. Thanks.